All right, everybody, if we could take our seats and we'll launch the next round of lightning talks. So hopefully we had some great discussion during the coffee break. So we will launch right into round two. So we've got another round of lightning talks, and then we're going to, right before lunch, the last 30 minutes of this session or so, we're going to be talking about the National Spectrum Strategy. So our first lightning talk is by Ismail from the North Carolina State University, talking about 3D signal interpolation and measurements with UAVs. And again, just to remind folks to keep us on time, I'm going to be hanging out up here. If you see me stand up, it means you're getting close to the end of your time. If you see me inch towards you, it means you're getting really close to the end of your time. So.
Thank you, Chris. Hi everyone, I'm Ismail Güvenç from NC State. So I'll present some updates from our platform. We had a supplement for NRDZ research with our aerial platforms at NC State. So very briefly, for those of you who are not familiar with AirPow, we are one of the 4 power platforms, and we are focused on experimentation with drones. So we have a flying field that is about 7 kilometers square. We have a digital twin where you can program the drones and wireless for spectrum research or 5G or experiments with LTE. And these are the 5 towers we have. You can fly drones as however you want, as long as you are within the geofences and the height limits. So I'll talk mostly about the interpolation aspect, but very briefly in the end about the spectrum measurements and modeling we have done. So our main goal is to use drones as spectrum sensors and interpolate the spectrum into the 3D space. It's not a trivial task because of the complicated propagation patterns in the 3D space. You have to get enough measurements to characterize the correlation. And towards the end, I will show some interesting results that even the orientation, tilt, and antenna or the patterns of the drone, they matter a lot. So a single map will not be sufficient. So maybe some of you may have, I presented in a past NRDZCOM these results, but what we are trying to do is we have some limited measurements, which are those circles with different colors. So you have, these may be RSRP measurements at a drone, and what we are trying to do is estimate the coverage at another location that the drone has not visited. So this is the whole 3D space, right? And for that, we are taking a circular, basically region, and then we are using certain number of measurements in that point to interpolate to that location. Oops, I didn't realize this is automated. But so if you have more measurements, obviously, we are going to have better interpolation accuracy. So we are using crying and its variations, as you can see in these results here. So if you have a radius of 200 meters where you are using points from and interpolating to an unknown location using crying, we use ordinary crying initially. You have better accuracy, but if you are using too many points, they also add noise. So this gives you the some intuition of, I mean, you shouldn't use too many points because the correlation becomes over, and it hurts your estimation performance. And if you are trying to estimate to a point, to an altitude that you didn't have measurement, so what I presented here was 30-meter altitude for the drone. If you are trying to interpolate to 50-meter altitude, you will have bad results. You come closer to the free space path-loss-based estimation that you see at the top there. So in the past year or so, we have done some extensions to the crying algorithm. So the first thing we have done is, and very quick, that there's a paper that was presented yesterday by one of my students. He should be somewhere here. So you can go to the paper in DySPAN for more details. But instead of ordinary crying, if you use simple crying, remove some constraints, you have better interpolation accuracy. And some locations in the 3D space, you also crying cannot extend to those locations, so we use matrix completion algorithms, and then you may, for that you need to also calculate the variance at each location, and then with that you can, with matrix completion, you can have further gains in interpolation accuracy. And the third thing that we have done is to transform the shadowing, the observations so that they are Gaussian distributed. So cryogene works well only if your data is Gaussian distributed, and we have observed that your shadowing is not Gaussian distributed. So this looks almost like Gaussian. It's a skewed Gaussian, but we have some other measurements. We have multiple bimodal type of distributions. So that transformation helps a lot with cryogene too. So if you do that, you have also significant gains. So we have some ongoing work that we haven't submitted yet. We are working on basically finalizing those, but we are taking into account the antenna patterns. Some of what I presented earlier, they already took into account antenna patterns, but this is what we characterize in an anechoic chamber for the combined. This is with the transmit-receive antenna gains multiplied. It's a combined antenna pattern. X-axis is the azimuth, y-axis is the elevation. You can see that it doesn't look like a donut at all. But once you attach this to the body of the drone, it becomes even more complicated. So the bottom part of the second figure there is the same as the first one because we don't have any observations when the drone flies. We captured this when the drone is flying and we did a lot of measurements. But the top part, you can see there is some similarity. On the top right, you can see some coverage, basically a weak coverage, weak antenna gain, which is similar to the what we characterize in the anechoic chamber, but it's also very different in general. So there are more weaker directions in the azimuth and elevation plane. So what it means is your antenna gain will play a significant role based on where you are with respect to your transmitter. And another important aspect is your orientation and tilt of your drone with respect to signal source. We had a competition in AirPower last year where we had 5 finalists and they were trying to localize an unmanned ground vehicle on the ground with a very narrow band waveform, 125 kilohertz. But if you check here, the transmitter on the first figure is an unmanned ground vehicle up there. And there are some crossover points. You can see that there is maybe on the order of 10 dB difference at the same exact point on those crossover locations based on your orientation, right? So if you are going in a different orientation, your signal may be almost 10 dB stronger. And in the second one, if you are flying towards the signal source or away from the signal source, the difference is even larger. So you may have like 20, 30 dB variation at the same exact location. So my point here is single coverage map is not good. So you should take into account the orientation and the tilt of the drone. And that should also help with your propagation modeling. And that's what we have been looking at recently. So this first figure is when we take into a radiation pattern from the anechoic chamber. The red is the measurement, the blue is our propagation model. You have some match, but obviously there are significant leaps, and those are because of those orientation differences and tilts. And if you take those into account, orientation differences into account, you get a bit closer. So we are still working on that, but we hope to characterize those signal dips much better so that if you know the orientation tilt and maybe some additional information, maybe we will better characterize those dips. How many minutes do I have? 1 or 2? Okay. So if I had 8 more minutes, I was going to talk about the spectrum part, but I only have a single slide. So we have done also a lot of measurements with our Helikite platform at NC State. We have done 3 rounds of measurements, 2 of them in an urban area in our main campus, 1 of them in our rural environment. When I say spectrum measurements, we sweep the whole spectrum from 100 megahertz to 6 gigahertz. And then we capture everything there, right? So we have all the 4G and 5G bands up to altitudes of 200 meters. And what I show here is just to highlight, they are representative results, just to highlight the importance of getting spectrum measurements at altitude. So the first 2 figures, they show measurements when your Helikite, when we aggregate all the measurements when the Helikite is about 50 meters. And these are measurements from 2022 and 2023. The blue is 2022, red is 2023. The first figure is C-band. For those of you who know what happened with C-band is after last summer, 2023, FCC and FAA, I guess they allowed to go up to 3.98 gigahertz, and you can clearly see that difference in the blue spectrum, right, 1 year apart. But if you do those measurements below 50 meters, it's barely visible. So that's very critical. So you might be putting even on a rooftop, and maybe you are not able to see what's the difference in the spectrum. So it's very critical to do the measurements at an altitude. And same thing goes for another band, 5 gigahertz, which was a Wi-Fi band. You can see that significant. Oops, I was deliberately not looking there. And that is my last slide. So we have all those. I was ignoring you, but and I'm finished. So we have all those data publicly available. If you go to airpower.org, you can access them. Thank you.
Okay, thanks, Ismail. And so next up is Dinesh from the University of California, San Diego, talking about sweep space. And yours is here.
All right. I have far too many slides as well, right? But I don't intend to go through all of them. But so just to introduce, I think Raghav, the student working on this, I think he has a demo as well outside. I think everybody can go by and see, right? I think he has a very cool demo. So he's the one who's doing a lot of the work, right? Akshit is the other student who has been working, right, with this. Abhishek is our postdoc working on this on our end, right? I think, and there are two other students from Alireza. I didn't have them because I think we didn't get those changes in. But so this project is jointly with me, Ramesh Rao at Aaron at UCSD, and Alireza at RIT. He used to be at CU Boulder, removed recently, and so Doug as CU Boulder as well, right? So let me, I think first want to say that I'm just a presenter here, right? Merely not in many capacity done a lot of work. So what was our broader goal, right? I think we have been trying to build a concrete tool which I think helps with all the directional sensing, right? Okay, and this could be the drone-based things, right? It's a fundamental sensor which basically transforms the way we sense everything, right? And this is needed because everything is becoming directional, right? Spectrum users, communication, satellites, or all of these are getting to directionality, right? And the space is the way to get to an infinite capacity for sort of what we can do with wireless communication, right? So in that regards, right? So the idea for this project was sort of, can we enable this very interesting and complex use case, right? So you have a radar, and it's a directional radar using some directionalities, and the signal sort of gets to a certain point, right? And then there is a base station nearby, right? It's also trying to communicate and sort of, just a second, let me get a laser pointer, right? And can we have them coexist very closely in the spatial domain, right? That's really the goal, everybody. And I think everybody knows here, right? I don't have to explain. There are three thrusts for our proposal, right? First, to build a really cool sensor, which essentially sweeps frequency. We already had that before we sort of submitted. Now it also sweeps space. That's the second part it does. So it can do a very low cost, very wide band sweeping of space, time, frequency, right? And give you whatever it sees as a directional insight, right? I think, and that demo is what we have shown today outside in the room, right? Next, you can get all these sensors collectively form and connect the information to a central unit, right? And that central unit then basically can provide you with additional insights of geolocation, where they are in 3D space and so on and so forth, right? And finally, you can use that to do things where you inform base station what it can do at what time frequency, right? And connect all of this fabric and do basically all spectral coexistence applications, right? So this is how we see these three thrusts, right? So I'm gonna skip a lot of these things which you have presented in previous NRDZCOMs, right? But the broad idea is that we are trying to build a very, very low cost sensor which can do time and frequency sensing, right? So I think we already have, I'm gonna go through directly the prototype, right? So this was inspired from our work Crescendo, right? I think, and this is also open source and publicly available, because I think a lot of colleagues asked me about Crescendo and they want to re-implement it, right? What it does is that it continuously sweeps frequencies and detects all the signals and does cyclostationarity for each of these signals and provides what additional insight it has, right? So that was what we did in like 2 years ago, right? Now, next, that's where sweep sense was, that is sense, not sweep space. Now this is sweep space, right? Okay. So that's what I think all of these things were done with Crescendo. So you can go look up Crescendo and you will find that paper, right? I think we have cool names every time, right? I think I create that way. It's easier to Google us, right? So now this is sweep space, which is inspired from sweep sense, but idea here is to sweep the space, right? And get very clear directional insight, right? And the last talk I had, last time I presented this rotating sensor, right? And this was really bulky, giant. I think it actually one time with wind it sort of crashed, right? Okay, so we had to give up on this, and this is where our next generation is now. So this next generation is fully digital beamforming based, right? It can do both frequency and space sweeping, right? And it has sort of a detailed complex design you can go look up, and I don't want to waste your time on that, right? I think just show you some cool hardwares, right? And it can also be arrange the antennas in L shape, and that gives you 3D sensing, right? So instead of just doing 2D, it can also do 3D. So here's what the final overall architecture looks like for generation 2, right? So basically you have a 2 radio, low cost software defined radio. You take those 2 channel, and this one channel is continuously switching to many, many antennas. So if you want 1000 antennas, you can put 1000 antennas here, right? And these are switching every 5 microsecond, right? So basically, if you have a signal which is 50 microsecond long, which is the smallest Wi-Fi packet possible today, right? Which nobody uses, by the way, it has 0 payload, right? Even that we can use 10 antenna to sense, right? So imagine all the emissions we have, right, are typically on the order of milliseconds, right? So if you want 1000, put 1000 antennas here, right? So this hardware is scalable first. Second, it goes through this real-time energy detection algorithm, right? What it does is that it takes the entire time frequency grid, cuts out every single blurb of energy, and compresses hugely the spectrum, and you just only have the IQ for each individual signal, right? It's showing that you just have only this signal, and that basically creates some time domain samples for it, right? Now you can do any additional processing you want on this one particular signal's IQ, right? And here what we do is that we are right now doing angle of arrival estimation. But if you want to do protocol detection, you want to do anything else, you can do all of those things, right? And then finally we take this angle of arrival, and here is what we are trying to get. So imagine I want this device in my living room, and tell me exactly what all devices are emanating, where are they emanating, what location they are, right? This is what we are trying to build as a fundamental tool, right? So it's showing me in a living room, I have a phone and I have a smart whatever light, right? And some other smart things, right? And when they are blinking, when they are not blinking, right? Are they stealing my information or not, right? We can do all of these things as well, right? Very likely they are, but still we can know when they are, right? So that's all we already have built, right? And that's what the demo is, right? I'm going to just play this video, right? Hopefully this plays. Is it playing? Sorry. Okay, it is. Yeah, it played, I guess. Wow, okay. Give me 1 second. Okay, in the interest of time, I think everybody can go outside and maybe just see the real video he's showing in real time, right? I think, but basically what it shows is, okay, now I'm not able to even advance the slides. Okay, laptop has crashed. No, not hasn't. So, okay, minute and a half. All right, I'm on a real crunch. So, right, so this is the setup, right? And here we keep doing energy detection. We detect almost every single low, weak power, high power, everything, right, out there. Like the only limit is that we get to ENR 7 dB. I think everybody uses SNR. That's a wrong thing to use, right? SNR integrated over infinite time can still be detected, right? So if you have a minus 100 dBm signal, which is at, or minus 100 dB SNR signal, which is integrated over a million years, you can still get that, detect that signal, right? You just have to integrate, know how to integrate, right? So this does a very good job, right? We can handle, the question is how long can we keep buffer, right? So now here we are showing a demo, right? So what we have is that this setup of phased array, as we rotate it, the device, even if you move it, the green dot will continue to track it, right? I do apologize, this is a very, very small form factor, right? Okay, but as you see, as you rotate it, now the device is continuously following the green dot, which is the actual device which is continuously transmitting, right? So, okay. With that, I think I can say and summarize in 1 or 2 slides. We have been doing, Alireza has been doing a lot of ray tracing based experiments to create with satellite, with radio astronomy setups and trying to see what type of problems they face, right? In addition to that, we have a spec space, which is essentially a mobile SDR. So you have a phone, you can connect to an SDR, and it can do entire thing what we are just showing, right? And do it, you can deploy as an app, right? A crowdsourcing based app, right? We already have an app demo as well. We did this at one of the previous forums. I forget what the name was. Finally, we have this mobile CBRS base station, which we have been moving around San Diego and have been collecting a lot of data. So for last year, we have collected 1 year worth of SAS data, right? And we believe SAS is really, really not doing the job, right? It's supposed to, right? Okay. So I just controlled myself right there, but I think you can read the 2 papers we have on this, right? I think this is what Ramesh is doing, right? Okay, and this is the test bed and the facility we kind of have used, right? And with that, I will leave it this. Okay, happy to take questions. Yeah. No time for questions.
So we'll get you a bodyguard to protect you from Andy Clegg. All right, next up is Hongwei Zhang from Iowa State University, talking about spectrum slicing for rural use cases. And your slides are up here.
Thanks, Chris. Good morning, everyone. So here, it's only 8 minutes. I'm going to just hopefully give you a teaser about what's ERA and what you can do with it, right? So ERA is a living lab being built out in central Iowa, and it's so far jointly funded by the POWER program and NERDS program. So it has some of the key features include having high capacity wireless access and XHAL platforms operating across a wide range of spectrum from low band of 800 megahertz up to terahertz bands. It has also both SDRs and COTS platforms. And as we'll share shortly in the context of this event, there's actually a lot of spectrum available there for us to play with. And also there's rich dynamics, real world phenomena that's there you can actually really try to understand. Besides on the technology side, we do have a broad stakeholder community that's working together from both wireless and application technology industries, local government and communities, right? So there's a rich stakeholder community that can participate in some of the even social economic studies too. So also we heard about the national spectrum strategy a little bit earlier, right? And so here's a table just showing how much spectrum is out there you can use. For example, I highlight this, by the way, my student, also my colleague Asana and Mokarang is here. So if you have questions about the details, grab us afterwards, right? So there are 2 bands, for example, you highlighted here in the 3.1 to 3.45 and the 5.0 band, right? So you can see that we did actually some measurement, temporal measurement. The percentage of time when they are actually used is very minimal, right? So there's basically just to give you a sense about how much is there, you can actually come and try out. Now, then you may ask, in the agriculture and rural settings, what are the potential use cases? There are actually some unique use cases which actually do challenge how we do spectrum allocations, even in the dynamic spectrum allocation today, right? For example, one of the leading use cases relates to agriculture automation, where you have fleet of automated ground and aerial vehicles and may need to get in the field for phenotyping or other tasks. But most time of the year, they are not there, right? So, but they just need to be able to access a sliver or the slice of spectrum when they need to fly or need to go into the field. So for that, there's actually the need for on-demand spectrum slicing for such use cases. Another, I think, potential leading use case in rural America is actually the fact that many small telcos don't have access to spectrum, right? So there's a dire need for spectrum sharing between the rural small telcos and those regional and national carriers, and which can be actually enabled by some of the emerging platforms like O-RAN platform, right? So of course we know that we have been talking about spectrum sharing. There are actually SAS that was mentioned that has been used, but of course it's not perfect, right? What you have is not perfect. This is just one example showing based on the current FCC ruling, right, how much, and with the transmission power you have, how much coverage you could have. But whereas in reality, you can actually use much higher transmission power without doing any harm to anyone at all. But that gives you much better coverage, better capacity, also reduce the cost significantly, right? So that you can potentially enable broadband everywhere, anywhere in rural America too. Now, to optimize the behavior of the spectrum sharing system, we need to have better models, better solutions. Just to give folks a little bit insight into some of the phenomena we see out there in Central Iowa, for example, we looked at the spatial aspect. So here we, just as an example, we did some spatial measurement of the throughput using one of the base stations we have at the Wilson Hall. And we looked at how you can actually model this in a high fidelity fashion. We first tried the traditional model, right, pass loss and all those, and turns out that didn't really work very well. So we started looking at the neural networks, and here's actually one exercise we did. Basically, one use a plain general basic neural network, and then another choice would be actually introduce some physics-based modeling in there using Laplace equation to model the spatial dynamics. And then what we all were able to see was that by combining neural networks and the physics-based informed spatial models, you can actually capture those rich terrain features that's there. As an example, this is one of the base station there, and then there's a water tower where we have actually user equipment deployed here. You can see the kind of the impact of the water tower about the surrounding throughput that you can see. And then if we don't use the physics-informed model, right, if we don't use the Laplace equation to help model correct the errors, this is what you get with the basic neural networks, right? So, which is actually far away from the reality, right? So that just gives you some insight into, on the modeling side, what can be enabled. And then there are some details, I think, in the interest of time, I'm going to skip details, but essentially there's actually much smaller errors, much faster convergence time by combining both neural networks and domain-specific physics models. So hopefully that gives you some insight about how you can use error to do spatial modeling and some of the challenges there. And then on the temporal side, right, there's also rich temporal dynamics. This is showing at one side, another side at agronomy research farm at the TV white space band. We measured over time the 40 TV white space channels and kind of showed the spectrum growing here, right? So basically, there's actually rich dynamics that have to be addressed actually. So if you want to actually, based on the TV white space band, I think there's about 50% of the spectrum is actually not used all the time, right? But to be able to effectively utilize them, we have to be able to understand the temporal dynamics and then take those into account into spectrum access management strategies. So essentially, there's actually a lot of real-world phenomena that you can actually measure, model, and analyze using error. And based on those measurement modeling, you can develop solutions. And you can also try out those solutions in the real world with real-world applications in the loop, right? For example, in error, you can have end-to-end, fully programmable ORAN experiments that's enabled. There are example experiments you can look at in our website. So essentially give you a lot of flexibility in trying out new ideas and new solutions. There are actually quite some experiments that's already happening there, and we have also examples in the Arrow website. You can go there and check out a lot of information there. If you have any questions, you can email us at e2@arrowwaters.org. Now, before I conclude, I just want to share this event we're organizing in the last week of August. So this is our second annual event. We essentially, it's a chance for us to bring all the Arrow users, researchers together, and also thought leaders across different industries together to figure out how we can use Arrow as a tool to build communities, to build solutions together. One thing that's actually interesting this year is that it's going to coincide with the Farm Progress Show. If you care about industry, like for us, you probably know Mobile World Congress, right? The Farm Progress Show will be the Mobile World Congress, but for ag tech. And it's within the area coverage range. We have a tent there. Actually, there's a tent at the show. And for folks who are interested, you can actually come join us. We can also feature your demos or whatever you want to show there. Please check out, there's a website for that, and we are actually welcome ideas about how to organize. We do intend to organize the event together with you, actually. Hope to get your thoughts. Look forward to hear from you. Yeah. Okay, thank you.
All right, our final lightning talk is Sam Edwards from Idaho National Lab. He's going to be talking about dynamic spectrum sharing field trials. And that's you. Does that work?
That's great. Good morning. I feel grateful to be here with all of you. This is a very exciting topic. National Science Foundation and White House have issued a clear call for spectrum innovations. And in response, University of Southern California, ISI, my colleague Eric Klein, and I have partnered to study how the 890 square miles available in the high Idaho southeastern desert might enable future research to dynamic spectrum sharing, which is that independent systems operate closely enough in frequency, space, and time that dynamic access methods are required to prevent interference. Now with this, spectrum sharing it's truly innovative, so it's important to be aware that NTIA and FCC spectrum management policies do not currently define or otherwise mention spectrum sharing. I point this gap out in front because Idaho National Laboratory is a federally funded research and development center, or FFRDC. And we're very accustomed to providing government and industry decision makers with research that otherwise can't, won't, or shouldn't be done. Idaho National Laboratory has already partnered with many federal agencies conducting innovative spectrum research. We've been authorized by NTIA to operate with a experimental radio station license, so we have broad and enduring flexibility to conduct innovative spectrum testing. We also perform thorough spectrum analysis before every test. And our testing flexibility is enabled by the remoteness of the INL site, which is set in a low caldera distant from urban, airport, or military bases. With over 20 years of experience in spectrum management and RF testing at varying degrees of sensitivity, including licensee outreach efforts, INL is a strategic partner for regulators that are seeking reliable data with minimal to low risk of non-participant interference. So I say all this, obviously, because I need to describe a little bit about INL. But my point is that test beds enable groundbreaking and edgy research, innovative research. I like to think of the spectrum management policy as a large, fast-moving airplane. It needs to turn course, but the air pressure on the ailerons make that difficult. Following this analogy, RDZs, and particularly the NEFC, the National Experimental Facility for Spectrum Innovation, act as trim tabs, which are those independently controlled tabs set at the trailing edge of the aileron that make the control surface easier to turn. Idaho National Laboratory and other RDZs would provide a relatively safe environment to gather objective data using repeatable methodologies in real-world conditions. We're positioned, because of that remoteness, to enable innovative spectrum research, which can help decision makers to realize different solutions to chronic spectrum management issues. And we have plans to begin this spectrum sharing testing in 2025. These 2025 extended field trials are very exciting. We've got customer funding to enable us to modernize and automate our spectrum test capabilities, or at least begin, to enable persistent spectrum sharing tests without compromising RF testing by existing customers. I'll get to that at a panel discussion this afternoon. As my first example, the White House's National Spectrum Strategy has identified 7.125 to 8.4 gigahertz band for a study of repurposing. Since DOE has the most frequency assignments, you see over 2,000, NTIA has tasked DOE to study the impacts of spectrum repurposing. Subsequently, DOE has identified INL as the lead for conducting fixed point-to-point interference to noise testing. Specifically, INL is charged to determine interference to noise ratios of fixed point-to-point microwave systems in the presence of high-power 5G and Wi-Fi signals. This 7 to 8 gigahertz band study will require investments in spectrum measurement capabilities beneficial to future spectrum sharing costs or tests. Also, this extended series of field trials will occur between summer-ish of 2025 and summer-ish of 2026. And it will involve several dozen existing 7 to 8 gigahertz point-to-point systems in the presence of 5G, Wi-Fi, and other potential interferers under real-world conditions. Therefore, this extended field trial provides the demand signal required for INL to innovate, automate, and evolve to balance the extended field trial with our traditional customers. You can't only meet the current test. You have to continue to meet all the tests in order to sustain a capability at a test bed. So, whoops. My second example in 2025 of enabling spectrum innovation testing is a 6 to 12 month field trial of an INL developed dynamic spectrum access method. This technology leverages a process of sensing approved spectrum bands and avoiding sensed interferers. The dynamic spectrum access waveform has already been demonstrated to customers as able to provide reliable high bandwidth communications with negligible interference. I'm talking less than 20 milliseconds. We sense you within 20 milliseconds, we move to another frequency. The streaming video undisturbed. Yet spectrum regulators and manufacturers of primary use radios that occupy the S or C bands need assurance that the technology won't cause harmful interference. So INL is making plans to conduct another extended field trial that would evaluate received interference by primary users under various weather conditions at a high number, think tens of thousands of iterations, to develop statistical confidence bounds. The challenge of running this large quantity of spectrum sharing trials, and by the way, I just said that we were going to run a year of DOE trials also at the same time, plus we have existing customers. Overlaying all of these is the demand signal that we need in order to innovate, automate, and extend our capabilities to enable future spectrum sharing tests over the long run. Planning details are still coming together for this and the DOE 7 to 8 gigahertz field trials. These planning details are an important input to the USC ISI and INL Strata report due to NSF in September. So I'd like to leave you with a question. How can we collaborate to benefit the National Radio Dynamic Zone? In this presentation, I've described INL's needs to automate processes and expand spectrum sensing capabilities. I have not emphasized our solutions. We need to work together. This is the time to collaborate. As one example, I want to harken back to Dinesh's presentation just a few minutes ago. We have multiple centers of excellence developing spectrum sensing solutions that range from the highly capable and networked to the crowdsourced, Manisha's work on spectrum sensing. We need a spectrum sensing program to unify these different potential solutions into an overall structure for awareness and application. Thank you for your time. I want to, I'd love to talk with each and every one of you, so please catch me on a break. And I think that now is the time to start collaborating on our technologies, standardizing our data formats, and creating the repeatable test methodologies which can help us to provide key stakeholders with reliable data to inform policy and investment decisions in the future. Thank you very much.
Thank you, Sam. So that wraps up our research and lightning talks. And we're going to shift gears here and move into talking about the National Spectrum Strategy and the role that nerds can, will, or should play in the National Spectrum Strategy. So we have two presenters from the NTIA Office of Spectrum Management. We have Paul Ransom and Nick Lesort. I see Paul. Where did Nick disappear to? Well, you can come on up. We'll give you some stage space. Do you want to take questions? Or do you just want to talk and have them come chat with you at lunch or something?
I guess I'll talk. Did you get my slides?
I did.
Okay.
And they should be, what did you call them? There's Nick. Here's Nick's slides.
I think I called them implementation overview.
I may just have to re-download it. Why is it not here?
Oh, NSS implementation overview.
Oh, there it is. No, that's not what I wanted. I wanted to download. Google has to advertise. All right, it's all yours.
I guess I'll work more on slide. Good morning or good afternoon, everyone. My name is Paul Ransom. I work at the Office of Spectrum Management and Strategic Planning Division, and I'm going to talk today a little bit, provide an overview of the National Spectrum Strategy. I'd like to say I thought those lightning talks were very interesting. Glad that I was able to hear those. I think we're all headed in the right direction. We understand the problem set, so very encouraged about what I've heard. Okay.
So it's up on. Of course, this is going to be difficult.
We can go here maybe to.
Oh, there it is. There we go.
Okay, I'll just speed right through. I got 15 minutes. Okay. Shouldn't. So the National Spectrum Strategy is the Biden administration's updated policy on modernizing, spectrum. It was released in November 13th of 2023, along with the presidential memorandum, which also was the Biden's administration's policy for modernizing our spectrum and the access to spectrum. Within the presidential memorandum, it called for an implementation plan of the National Spectrum Strategy some 4 months or 120 days following the release of the National Spectrum Strategy. And it also called for the Secretary of Commerce through the NTIA to develop the National Spectrum Strategy and then ultimately develop the implementation plan 4 months later. That was done within the Office of Spectrum Management, primarily within our organization. Daunting task, to say the least, to write a strategy and then an implementation plan 4 months later. Happy to say that we think we did a pretty good job. The implementation plan is essentially the implementation of the National Spectrum Strategy. National Spectrum Strategy really focused on 4 pillars. Those 4 pillars were ensuring a spectrum pipeline to kind of meet the needs of the nation in terms of spectrum. There's a pillar 2, really focused on long-term spectrum planning. How are we going to improve long-term spectrum planning such that all the needs of the country are included and considered as we decide how we're going to make spectrum available. Then there's a third pillar. That third pillar was really about using advanced technology to improve access. And then there's the fourth pillar was around the spectrum workforce and expertise, ensuring that we have the capacity, the human capacity to meet our needs as it relates to spectrum. So ultimately, that was big picture, primarily what was in the strategy. As I say here, the implementation plan was really outcome focused. At a high level plan that was really organized around the National Spectrum Strategy's 4 pillars and ultimately 12 strategic objectives. Within the Office of Spectrum Management, our organization is essentially the steward of the implementation of the National Spectrum Strategy. The implementation plan, the way it was organized was that there were these outcomes that were organized around the pillars and the strategic objectives. Those outcomes, there was a brief description of what it is we're trying to achieve within the outcome. In addition to a brief description, it had a section where we identify what we were calling a responsible agency. So each outcome had an assigned, designated responsible agency, along with contributing stakeholders, which didn't necessarily have to be, federal agencies. In addition to that, within the implementation plan, we designated a time frame for the execution of those outcomes. Now, as I said earlier, the Office of Spectrum Management is essentially the steward of the implementation of the strategy, regardless of if we are the responsible agency for that strategy, for that particular outcome. We see the Office of Spectrum Management as having that responsibility. And I will tell you, it has become an all-hands-on-deck effort. We are some 2 months into the implementation of the National Spectrum Strategy, and it is that an all-hands-on-deck effort. It's a big job. It's a lot of work. It's a lot of planning. There's significant opportunities within the Office of Spectrum Management, given this this major challenge that we've been given. And certainly I would encourage those in the room and folks to take a look at the Office of Spectrum Management, NTIA, because there are certainly opportunities to join us in this effort. So what more to say about the strategy, about the implementation plan? So this presents essentially all the outcomes kind of on a time scale. So you could see we designed the implementation plan to look out over essentially like 3-year cycle. What can we achieve in those 3-year cycles? Well, how might we do that? And so here we try to essentially take the implementation plan, put it on a chart, and we can see kind of what are the near-term outcomes versus kind of more midterm or longer-term outcomes. Nick's going to talk about in the next 15 minutes Pillar 1, essentially focusing on Pillar 1 is about the spectrum pipeline. Within the presidential memorandum, there was a charge to identify at least 1,500 megahertz for study for expanded use, expanded access, and those 1,500 megahertz that were charged to the Secretary of Commerce and NTIA to identify for study were identified within the National Spectrum Strategy and also defined in detail what that study process looked like within the implementation plan. I'm not going to steal any of Nick's thunder, but those spectrum bands, there were 5 ultimate spectrum bands that were identified within the strategy and further defined within the implementation plan. He's going to talk about one of the bands for study, which is the 7 to 8 gigahertz band, 7125 to 8400. The process by which that study is going to be conducted. It's a very interesting talk. I look forward to hearing it. And so, as you see here, that was a part of the implementation plan, and specifically, I think that is outcome 1.2C, the completion of these so-called band studies. As we continue along this 3-year cycle of executing the implementation plan, there will certainly be more information about the certain outcomes that are being studied, and I'm sorry, not studied, the outcomes that are being addressed as we move forward. I'm gonna talk a little bit about one of the well, I'll briefly highlight one of the other outcomes that is, I think, particularly important to this group, the National Radio Dynamic Zone, which is the outcome on the National Dynamic Spectrum Sharing Testbed. That was, again, identified within the National Spectrum Strategy. It has a timeline of 18 months for its establishment and implementation. There's a talk later today on testbeds where we'll get into that, into the details, perhaps on a high-level discussion about what does it mean to have the establishment or the implementation of a dynamic spectrum sharing testbed in 18 months. It's a daunting task, and it's not as if we're going to try to have a completely finished testbed within 18 months, whatever that means. We'll talk about it more, but the idea is to develop a coordination process for how might a national dynamic spectrum testbed be implemented. What might that look like? Is it a singular site? Obviously, there are already a number of testbeds that are in existence, perhaps not specifically dynamic spectrum sharing, but have a capability. And within the implementation plan, we define it as essentially a federated network of complementary sites. So the idea is that there is not a singular place where dynamic spectrum sharing occurs and that becomes a national dynamic spectrum sharing testbed. It's a network of sites that work together to provide a capability for the nation. How much time do I have left? 5 minutes. And so this is that discussion on what that high level, what that testbed might look like. I guess I'm open to any questions at this point. I really didn't want to get into any more depth.
We have a microphone up there. See Sam is over there. Or, yep.
I think they're. Are you okay?
Whoever gets there first. How about I talk to you right here on the mic? Back up a little bit. Hi, Paul. What's that?
Wrote it down.
I did. I thought about this in advance.
Okay.
Well, I mentioned just a couple minutes ago that NTIA and FCC haven't defined dynamic spectrum sharing or spectrum sharing at all in regulations, right? So, but I have heard that there may be a definition that's floating around for congressional recognition, which would be really important. I wonder if you can give us any update on such a definition or what that might look like or sound like.
Well, Sam, that's a great question, and certainly there are a number of definitions that have been floating around that talk about dynamic spectrum sharing, and it is important to have a definition that is broad enough to include all the capabilities I think should be a part of it. One of the things that I like that I've seen and I've heard is that this group and nerds might want to offer a definition that is one that is coordinated in a collaboration amongst all the folks that are part of the spectrum sharing community. I think that's the most appropriate way to go. I hesitate for NTIA or Congress or somebody to dictate what that definition down to the experts. I think one of the smart things that you guys could do as a community is to develop that definition as a community through collaboration, and then that I think might lead to the best outcomes and results. So perhaps that's a charge for this group to help us define what that should be.
Hi, yes, I had a question. I think I've asked you, Nick, this in the past. In terms of, I think it's pillar 2 or 1 maybe, what is the spectrum pipeline for under NTIA, the federal agencies, obviously we know the most about DoD, but DOT and other agencies are pretty important spectrum-dependent operations too. What should we envision in terms of the overall occupancy of all the agencies into the NSS?
It's a great question. And you're right, it is spectrum, it is Pillar 1 and some of Pillar 2. So the way the strategy was written was Pillar 1 was really looking at trying to meet near-term needs, and that's why those 5 bands were identified for expanded use and study. And like I said, Nick's going to talk about the study part for 7 gigahertz. In terms of, you know, on the federal side, how is it that we're ensuring that there's a pipeline to meet the needs of the federal agencies? I think that's really the focus of Pillar 2, the long-term spectrum planning. The idea is that we're bringing together stakeholders from both industry and within government to bring their requirements forward, to establish a process by which we ensure that those spectrum needs are being met through this idea of long-term spectrum planning. You know, part of Pillar 2 identifies what we've called a collaboration framework, and then following that collaboration framework, using that collaboration framework to inform this long-term spectrum planning, essentially providing an opportunity for all the stakeholders to bring forth their requirements in terms of spectrum, and then work together to ensure that we have a plan to meet the spectrum needs of all the stakeholders. So you're right in sensing that is a pipeline for federal agencies in Pillar 1? Is it in Pillar 2? I like to think of it, we're talking near term, it is a Pillar 1 idea. If we're talking, you know, over the long term, we're looking at Pillar 2, long-term spectrum planning, being our approach to, you know, meeting those needs.
That's all the time we have. So thank you, Paul.
Sit over here. Sure.
So Nick Lesort, also from NTIA OSM, has the unfortunate distinction of being the last thing standing between us and lunch. Is he done?
We're done.
We're done.
Let's go to lunch.
All right.
Perfect. Chris, thank you very much. So there's a story that I love, and it's essentially when Marie Curie was 4 years old, like she stumbled into her father's lab, and she looked at this glass case, and there was all these test tube and like chemistry equipment. And as a child, like she came back to that room time and time again, like, oh, look at all these great things, like all the experiments that I could run with these. And like that childhood like fascination, like then of course propelled her to win Nobel Prizes. So really, I feel like a child whenever I come to these things like Spectrum Week. So again, thanks to John Chapin, like I don't think you understand how much of an advocate he is for you guys in terms of spectrum advocacy. Him and Jonathan Williams, yeah, Ashley. NSF is really the silent unsung hero for this. So I just wanted to like let them know it really is amazing. Yeah. Yeah, and I don't know what Paul thought I was going to talk about, but John sent me an email a month ago, and he was like, oh, could you talk to these two things? So if you love it, you can thank John. If not, you can blame Paul or me. And of course, Andy, I love your SAS. It's doing a great job, despite other comments. Let's just say that on the record. So yeah, so the two ideas that John wanted to talk about, what typically happens in a band study, and then maybe what are 3 possible challenges that the 7 gigahertz band study is going to probably face, or maybe face. And so what typically happens in a band study? So there's essentially 3 things. First, we identify all the federal incumbents in the band, right? What needs to be protected? Who needs to be protected? where are they operating at, how often, right? We just saw the slide about in the 3 gigahertz band, it's not 24/7 in some cases, in other bands it is, right? So we do want to identify that, because that's a key piece of information to give to our FCC folks. The second step is creating a link budget, right? The foundation of all spectrum studies is the link budget, right? So we iteratively work through that. How do we protect the federal incumbents from harmful interference? Typically, this is an agile process, so we are meeting every 2 weeks with the agencies, with the technical folks, sharing data, sharing code. They're seeing the report in real time. Typically, we may go through 20 to 30 iterations of a report just for the body of the report. Of course, the executive summary also goes through like 20 to 30 iterations also. Yeah, so we share code and data. And then number 3, we provide options. So really, the process is about feeding the FCC their report and order or their NOI or notice of proposed rulemaking to give them options to at least, or initial options, so that the public then can comment on that, right? Yeah, if we just look at like an example maybe of, oh man. So if we think about like CBRS, we did a study in 2010, exclusion zones, right? They came back to do another study. They were like, oh, try again. 2015, they did low power. The exclusion zones got smaller. Then 2018, they were like, oh, what about dynamic protection areas? So we did another study in 2018, right, to then feed the RNO, and now we're still doing studies to improve CBRS, right? So like, it's not just a one and done study, right? It's a very incremental process. We see that in other bands too. So the other part is, yes, 3 possible challenges that we might see in the 7 gigahertz study as we're going to this. Yeah, Sam, I'm excited about the experimental work that you guys are doing at INL. I think that's going to be great. Yes, a large part of the 7 gigahertz band is fixed point-to-point, right? Agencies, almost every agency has some sort of fixed point-to-point link. Well, not maybe every agency, but most. So yeah, that's going to be great work, instrumental work. I am very excited about that. Yeah, yeah, can't underestimate how excited I am about that work. So there's 3 challenges, essentially. The first challenge is, how do we get the right people in the room? We really struggle with spectrum studies. Everybody's focused on, oh, how we're doing it, but it really is just, oh, well, we need to find the experts, the right technical people, bring them into the room, because if we have good ideas, a great set of people can at least improve those ideas, right? Or throw it out and come up with a better idea. But if we have, you know, if we just put Nick in a room, he doesn't have great ideas, and yeah, it will go to bad. So yeah, just getting the right people in the room. Number 2, how might we enable frictionless reproducibility / peer review, right? So how many in this room have taken part of a spectrum sharing study? Raise your hand, anybody? Yeah, and so keeping those hands up, how many people were able to frictionally reproduce all those studies? Yeah, okay, yeah. It is a very hard thing to do. At least in terms of our federal studies, NTIA does the initial study, and then of course every 2 weeks we're feeding it back to the agencies. They have questions, concerns, we try and raise them, and that's just the agile project. It is very hard for them to break out of a waterfall project management mentality to then go to agile. So yes, how do we create this? And in that is, of course, how do we share data amongst ourselves, right? The underlying data of the spectrum study. And maybe challenge number 3 is, so in the 3 gigahertz, maybe you've heard the DoD has their moonshot, where essentially they're sensing, where the base station is sensing a high-powered radar, and of course, it's Uni 2 DFS all over again, right? But in 7 gigahertz, we don't have high-powered radars, right? So this makes it tough. So how do we share with an incumbent that we really can't hear, right? So this is, yeah, I'd love to hear ideas on how we might share with the incumbent with that. So yeah, join us in the upcoming band studies. Make sure we're getting involved. I don't know when the multi-stakeholder group is happening, where, or specifically with what organization, but hopefully midsummer, they say, but definitely get involved with that. Yeah, and that's my time. If we have any questions.
Just wonder, you mentioned the reproducibility. What are the key
Yeah.
challenges or barriers you see so far that, if addressed, can help enable that?
Yes, so the way we try to address that is any study that we do with the agencies, I upload all my MATLAB code to GitHub first. So they can download that code, run it on their own. So that's how we try and address the reproducibility issue, at least. Some folks don't like MATLAB, so we print out Excel sheets where it has each link budget line by line, right? The power, transmission loss, lat longs, heights. Yeah, just so any way to help people understand what the analysis is. Yeah, we're always flexible in trying to help others understand. But yeah, I'd love to.
So this might be maybe not the question which maybe your team handles, but so let's say once the spectrums are allocated, right? How well are they used, right? Who is like measuring this? I think, and I do see a lot of data for ourselves in San Diego, and I see lots of bands are not being used effectively, right? And one might wonder, like, do we even need these new bands, right? But I think, again, this is where if you are just going to create industry.
Is it an exclusive band or is it a shared band that you're talking about?
Mostly we are just looking at the licensed bands of
Okay.
LT,
Yep.
where we see a lot of time the utilization is very low on the band, right? But the industries keeps asking for the new bands, right? So I'm just trying to understand, like, is there a charter within NTI or somebody to sort of, once these bands are allocated, who is trying to profile how well they are used across space, time, frequency?
Yes, so the identification of the bands, like Paul said, was the president, and then, yeah, he told us to study it, so I don't know what to say.
Yeah.
Oh, auditing, yeah, that's a great question. I know the FCC has build-out requirements in terms of the non-federal folks, but we don't have build-out requirements of the federal folks. So,
Can you hear me? So that's a really good question. And within the implementation plan, a part of one of the outcomes was about understanding better, potentially developing a kind of spectrum monitoring program or a spectrum usage program. It's one of the outcomes. It's an outcome, I think, in the more midterm, essentially trying to develop a program that helps us understand that more. And you're not the first person to ask, what is the utilization? What are we doing about understanding it better? It's certainly a part of the implementation plan and the development of a program that kind of helps us try to figure out how to establish a way to get that information more consistently.
it's a very hard problem for when we think about like federal systems and radars. Of course, some are not on 24/7 in a fixed location, so it's very hard to sense that, right? So, yeah, it's in terms of a federal band usage, that's something. Nisha.
Actually, a follow on to what Dinesh just asked is, so right now, the band study that you're doing, is it focused on allocations or usage? So are you really looking at what has been allocated, or are you also looking at whether all these allocations are actually being used by the federal services? That's question number one. Second one is, you mentioned fixed links. I assume the fixed links are very similar to 6 gigahertz fixed links, except they're federal. But what about the other users, the satellite and all of that? And when does this information become available to us non-feds?
Yeah, so the table of allocations is a great place to see what is in the band. Of course, you'll see space, space research, fixed satellite, fixed, But back to your first question, what was your first question? Sorry, Manisha.
Allocation versus
Did you-
usage.
Are you just looking, when you're doing this band study right now, are you just looking at allocations or are you actually looking at usage and how much of this federal band is being
Yeah.
used?
So it's a bit different. So if we think about it in terms of the FCC rulemaking process, so our first job is to identify the federal systems, right? So yes, maybe it's NASA at Goldstone. We have to say, well, here's a federal system in the band. This needs to be protected, right? So that's essentially the underlying data to any NTIA submission to the FCC, right? So it's not necessarily, oh, are they using all the band all the time? But yes, we hope to get some of that data like, so fixed point-to-points, yes, they essentially use it 24/7. But if we think about like radar systems in other bands, yes, in some cases, they aren't using it all the time, so it's good to know when and where they're using that, right? But in other bands, 2.7 to 2.9, the FAA is using their radars 24/7, right, in fixed locations, or NOAA weather radars, right? That's 24/7. So there is this dichotomy of spectrum usage that we see with the spectrum user. But getting some of that initial quantification is definitely
So
what we yeah.
Oh, sorry.
It allows the non-federal users to then see, oh, well, how much opportunity to spectrum access would I have, right? If we come back to CBRS, a ship is not always along the entire coast all the time. So when can they share? So that's, if that kind of hits at your, yeah.
All right, I guess we'll let Paul have the last word.
Really love your question, Monisha. At a high level, the implementation plan defined an approach to band studies in the appendix. And it talked about, there was a section that talked about non-federal participation or contributions to the band study, which suggests that, you know, we're going to conduct this band study for these bands that have been identified and look to set up a process or a way for us to get contributions from, you know, non-federal stakeholders about, you know, how might we more efficiently share the band? What are the ideas around, you know, how do we ensure that the access, you know, that perhaps we're looking to give non-federal users meets their needs? So there will be later in the summer, there will be a standing up of a way for non-federal stakeholders to really contribute to the study in a way that gets to, I think, Nick's first issue about the challenge. So stay tuned. There was a blog that was also released, I think, maybe 2 weeks ago, that alluded to that that NTIA, the Office of Spectrum Management, is looking to set this up to allow for those kinds of contributions from stakeholders and experts like yourself. So.
All right, well, we are officially at time, so thank you, Nick and Paul. So we will reconvene promptly at 1:30.